So the topic for today is protein electrodynamics in Terahertz Medicine, new paradigms for medicine and COVID-19. As mentioned, this is a specific area in bioelectromagnetics, which has been the subject of this course for the past semester, but it brings together many concepts in bioelectromagnetics in today's lecture. So I'll begin with a quote. Two things filled the mind with, ever new and increasing admiration and awe. These are the starry heavens above and the moral law within. This is Immanuel Kant in the Critique of Practical Reason in 1788. Two things fill the mind with ever new and increasing admiration and awe: the starry heavens above and the moral law within. This doesn't sound like a very scientific concept. It's a favorite quote of mine, but later on in this presentation, it'll be very clear why this quote is relevant. So the outline for today's discussion will be a background, some science, and applications. So three parts: background, science, and applications. So by background, we'll talk briefly about the future of diagnosis, the future of therapy, the future of technology, and how does life work? These are motivating questions for much of the presentation and discussion to follow. So what is the future of diagnosis, specifically with respect to imaging? We've talked about X-rays during the course. We've talked about MRI, PET scanning, and so forth. And many of you are familiar with this chart. We have the four major modalities of X-rays: ultrasound, MRI, and PET. And you can see that they were founded in many different years. X-rays over 100 years ago, PET scanning in the 1950s and 60s, and so forth. But what's interesting to note that these four major modalities, which we discussed, except for ultrasound, of course, there's been no new modalities since 1985. In other words, many of these innovations that you may have heard about, such as diffusion MRI, multi-slice CT, PET CT combinations, these are incremental innovations, not fundamentally new modalities. And we need some new approaches to imaging, some new approaches to diagnosis. We have another very interesting phenomena in the realm of therapy. In medicine, we have diagnosis, and we also have therapy, and we've talked about many of these electromagnetic approaches to therapy. Of course, the major approach to therapy is using drugs, and of course surgery as well, which we'll mention. But on the pharmaceutical side, there has been an interesting trend. This is the number of new drugs per research dollars over the past half century, and you can see more than a half century. It's a Nature article. You can see that there has been a continuous monotonic decline in the efficiency of research in this area. In other words, there have been less and less new drugs coming out with more and more research dollars. And in the year 2000, it cost about $1 billion to create one drug. So again, apart from incremental advances, innovation in biopharma has also stalled. What is the future of technology? And this is a very broad question. There are actually some very interesting ways that we can predict the future of technology. In fact, there are methods called TRIZ and so forth, TRIZ, which predict the future of technology based on the past. In other words, there are patterns of technology evolution that have been fairly regular, fairly predictable, which make the future actually not so difficult to predict. In other words, for example, you know that telephones have gone from wired or landline phones to wireless or mobile phones. And likewise, you can see in this chart different technologies going from immobile systems to eventually electromagnetic or force field-based systems. So here we have, in the case of steering, a rigid steering wheel, ultimately leading in a set of progressive evolutionary steps to electrical steering. A simple technology such as a door also progresses to becoming more mobile, more flexible, and a single leaf door eventually becoming a light lock like in Star Wars or Star Trek. So if we look at medicine, the current technology in medicine is what we would call a matter-on-matter paradigm. A drug binds to a protein, or a device or a hand does surgery. By matter on matter, I mean there has to be a physical connection between the two. Of course, all of you in Bioelectromagnetics course know that we have what's called an energy on matter paradigm. We use methods of energy to either diagnose or to cause some therapeutic effects. And we've talked about radio frequency ablation. We've talked about lasers and so forth. Actually, lasers we'll talk next week. And obviously, we've talked about X-rays as well as therapeutic methods. And as we'll discuss shortly in this presentation, these are indeed electromagnetic methods, but they have their effect through physical mechanisms. What I'm talking about is, and we have not explored until today, biological methods of electromagnetic interaction. Of course, actually early on when we were talking about 5G and so forth, we talked about some biological interactions. But in general, a lot of that was more speculative and certainly not part of medical practice. So that is the issue. What is the future of technology? And the point will be that if we look at these natural evolutionary progression of technology, the future will be some form of energy on matter interaction when it comes to medical therapeutics. The final motivating question is, how does life work? And this complicated spaghetti is what we call an interaction map or interactome of all the proteins from published interactions in I believe this was yeast. And so this is the interactome. And what this diagram is meant to portray is how complicated and almost seemingly random are these interactions, and how does life work? It works by proteins interacting with each other and causing various results. And what this interactome suggests is that those interactions, which result from the semi-random or random bumping together of proteins, is pretty incredible. It's pretty incredible. How can life work? How can I speak? How can you listen? How can you hear? How can you understand? How does this happen? To arise from the essentially random three-dimensional motions of proteins bumping into each other is very hard to imagine exactly how that happens in an organizer. We know it does, but there must be some other processes involved. And I'm not talking about religious issues and so forth, but other scientific ways that somehow these proteins are interacting efficiently, effectively, and in some way. And so we'll talk about how these concepts may lend some insights into this fundamental problem of how life can work in all this mass confusion and at the speed of real-time life. So where do we go from here? What will be the future of medicine and healthcare in terms of diagnosis and treatment? And how can we better understand the fundamental mechanisms of life, in particular those that are driven, and very importantly driven, by the interactions of proteins with each other. So the story begins over 30 years ago, and this is what has brought me to this field of bioelectromagnetics. I was a college student just like yourselves at Harvard, and I did my senior thesis, my final year research work with Professor Martin Karplus, as shown here, professor of chemistry at Harvard. And Professor Karplus was one of the pioneers in what's called molecular dynamics. And molecular dynamics is a simulation of biological macromolecules, in particular their vibrations and motions in space. And I'll never forget Professor Karplus. He was introducing me to his research group. I was sitting there at his table, and he was telling me that proteins are neither solids nor liquid. They are something in between. And that was a very fascinating concept to me at that time. I thought that was very interesting. And I did work with him. And then as you'll see in this next few minutes, the implications of that statement. So now we get to section 2 of the presentation, some basic science. I'll start with the axioms of protein electrodynamics. What are proteins? Terahertz Medicine, protein dynamics, some scientific questions, electromagnetism and terahertz, and some scientific results. And finally, some conclusions and technical challenges. So proteins, what do they look like? Well, they are macromolecules, large molecules. Here are some examples of myoglobin. It's an oxygen carrier protein, or it's actually oxygen storage protein. It's mostly what we call alpha helix. Here's another protein, basic fibroblast growth factor. It's mostly beta strand. These are actually proteins that I've worked with during the course of my research career. Here's some other proteins, the androgen receptor, human growth hormone, also both of them fairly alpha helical. And you can see this is what we call a van der Waals surface representation of the protein. This is what we call a ribbon diagram of the protein with the backbones and so forth. This is the surface. And the point of all these little pictures is to indicate that these proteins have many different sizes, shapes. The formal term for that is conformation. They have many different personalities, and they look very different and obviously very different functions. So what do these proteins do? Well, here are some types of proteins and their function. There are structural proteins that cause support. These are like collagen. There are storage proteins, storage of oxygen, as I mentioned. Transport proteins, hemoglobin transports oxygen. There are also transport proteins for other substances and molecules. Hormones, receptor proteins, the androgen receptor that I pointed out, in which protein is on the surface of a cell and another protein will signal some message to that cell through binding to the receptor protein. Contractile proteins, that's how muscles work. There are proteins in the muscles that are obviously mediating that contraction. There are defensive proteins, such as the antibodies, very important in COVID and any other infectious disease, and enzymes as well, which will catalyze reactions and do the metabolism of life. The short story is that proteins are essentially the machinery of life. And it turns out, of course, that many drugs will actually bind to proteins. And that's how they can influence these functions. And in disease, such as cancer, where there's too much growth of cells, you can bind to certain proteins and affect those proteins and cause the cancer to slow down and so forth. So drugs function by inhibiting or stimulating these proteins. Many drugs do. So here's an example of a protein, just to give a sense of the personality involved, that they all have a different character, if you will. This is a voltage-dependent potassium channel. You know about this protein. This is the protein that brings down the action potential we discussed in the beginning of the course. And you can see it is shifting. I showed you this diagram during our course, or that lecture, and it shifts from an open state to a closed state. So there are definitely protein dynamics occurring. These proteins are changing in their shape. They're changing in their conformation. So the axioms of protein dynamics are as follows. First, these proteins vibrate, and you can see, I hope you can see if you have a computer. It might be a little bit more difficult if you're on a mobile device, that this protein is vibrating. The second axiom is that the proteins are charged. They have positive or negative charges. This is acetylcholinesterase. It has a negative charge in this center binding pocket and it has positive charges around that. Acetylcholine, which is the substrate, is positively charged. It's a quaternary amine, and it will bind in that spot here. The mathematics of modeling these charges on the surface protein in a static sense are given by the Poisson-Boltzmann equation. And the third fact is that of Maxwell's equations, which we also went over in this course. Maxwell's equations, as you know, lead to the production of electromagnetic radiation through the acceleration of charges. Charges are moving, a magnetic field is created, a changing magnetic field will create a changing electrical field, a changing electrical field will change the magnetic field, and so forth. And that propagation, which we have talked about earlier, is an electromagnetic wave. And so vibrating charges, oscillating charges, or dipoles, which are separations of charges, as you know, will create electromagnetic radiation. Therefore, point number 4 is that proteins emit radiation. This is an article which we'll talk about shortly. Terahertz radiation from Bacteriorhodopsin. And proteins also absorb radiation. This is optical measurements of long-range protein vibrations. And we'll talk about this protein as well. So the axioms of protein electrodynamics: proteins vibrate, proteins are composed of charges. The laws of electromagnetism describe the implications of that, namely that proteins will emit and proteins will absorb electromagnetic radiation. So you can see here's a protein with charges. Radiation is given off as denoted by Planck's constant times the frequency, and then of course radiation is also absorbed. This is the essential idea. So let's explore this in a little more detail. So as I mentioned, Martin Karplus and others taught us that proteins vibrate. This is the original article in Nature with Andy McCammon, Bruce Gellin, and Martin Karplus. Now, I have an interesting personal story. I never met Bruce Gellin because I joined the lab actually in 1985, almost 10 years after they did their work, and Bruce Gellin had gone on. And just recently on Facebook, Dr. Gellin and I have connected, and we started talking about things, but that was interesting. But Martin Karplus, of course, was the professor, and for this work, he actually got Nobel Prize in 2013. He shared that with Michael Levitt of Stanford and Aryeh Warshel in Israel, and they were founders of protein dynamics, molecular dynamics more generally. So we know these proteins vibrate. In this case, it's bovine pancreatic trypsin inhibitor. And the next question is, so they're vibrating. We know that. They have molecular dynamics. That's been well established. What are the frequencies of these? So here is a paper. It's also an older paper from 1990, but it is with Jeremy Smith, Christophe Coursera, and Martin Karplus. Christophe is now at the University of Kansas. Jeremy Smith, also a friend of mine, and he's now at the University of Texas. You might have seen an article about COVID-19 molecule simulations on supercomputers to get drugs designed, and he was the leader of that study. It was published in Nature just a couple of weeks ago. And we're also in touch, Facebook friends and all that. And of course, Martin Karplus. So what is the importance of this paper? There are many examples, but I wanted to just give one example. First of all, it's myoglobin, as I mentioned. It's a protein. And it's a comparison of simulation results with neutron scattering spectra. Neutron scattering can be used to detect these protein dynamics. So this is the theoretical simulation from the molecular dynamics simulation of Martin Karplus. So the program is called CHARM. And these are the experiments with neutron scattering at the ILL, Institut Lagrange. And so these major frequencies correlate. 15 to 20 centimeter, inverse centimeters corresponds to about 450 to 600 gigahertz, 0.45 to 0.6 terahertz. Gigahertz is 10 to the 9th cycles per second. Terahertz is 10 to the 12th cycles per second. So we can say, roughly speaking, that this is in what one might say is the sub-terahertz realm. So let's look at this. Now, proteins are also generating heat, are also molecules, obviously, and all molecules have some bond vibrations. That is the nature of heat, infrared radiation. We have studied this at length in this course. Infrared radiation is a result of molecular vibrations. And in fact, when they use the temperature thermometers, the thermal scanners for checking your temperature because of this pandemic, they're picking up infrared radiation. And like all molecules, proteins also have these vibrations. So what is the difference between the vibrations related to terahertz or sub-terahertz, and what are the difference between the vibrations that are related to infrared? So the electromagnetic range terahertz is what we would call low frequency, and infrared is high frequency. Now, of course, this is relative terms compared to radio waves. Both of these are very high frequencies. We talked about radio waves also at length. These are in the hundreds of hertz or thousands of hertz, kilohertz or megahertz. So this is low frequency, relatively speaking. The type of motion of terahertz are these large scale motions, the one you saw, for example, with the potassium, voltage dependent potassium channel. And the high frequency motions are these backbone and small groups of atoms in the individual bonds. Those are the ones that give rise to infrared radiation. So both of these motions will be sensitive to conformational change. In other words, if the protein changes a lot, they will change both the infrared and the terahertz. On the other hand, these very high frequency motions are very similar among different proteins. So if we want to distinguish between different proteins, it will be very difficult to do that in the infrared. Now, if we want to diagnose different proteins, if we want to see different proteins in different cells and so forth, we obviously will want to electromagnetically distinguish between them, and therefore this low frequency terahertz motions will be more applicable to medical diagnosis. Now, also, if we're looking at the functional significance of the motions, these little, very small vibrations of individual bonds and backbone and so forth are not relevant as much to the function of the protein. If you think of an ion channel moving, big movements, or you think of a receptor having a conformational change, or tyrosine kinase, or induced fit mechanism with an enzyme such as hexokinase and so forth. These are all large-scale, low-frequency motions that underlie the functional aspect of the protein. The infrared motions are related, but are not essentially functionally significant. So if we want to alter the function of a protein, in other words, do a kind of therapy, we want to be doing that with respect to those types of motions, which implies that the low frequency terahertz is going to be relevant for medical therapeutics. So, infrared is sensitive to small changes in the backbone atoms, which are these backbone motions, but the differences between proteins are washed out. With terahertz between proteins, even similar ones, differences will be apparent, and this is a hemoglobin myoglobin study that I will talk about in more detail. And large-scale motions are responsible for protein function. So this is another Martin Karplus paper, Molecular Dynamics and Protein Function. And again, I will talk about these in more detail. So this whole axioms of protein electrodynamics creates several scientific questions. And so let's go through some of these questions. First, do different proteins vibrate at different frequencies? You might say, you might have been noticed that at the beginning I showed several different proteins, the myoglobin, the basic fibroblast cofactor, the androgen receptor, the human growth hormone, etc. I showed these different proteins, and I suggested that they have different shapes, different personalities. There's great diversity. And in fact, the reason I mentioned that is indeed that diversity is manifested in very different frequencies for their electromagnetic manifestations. So the answer is yes. Different proteins do vibrate at different frequencies, and I'll show some examples of that. Second, can we identify different proteins based on their spectrum? Yes, but it will not be easy for now. And so the answers to these two scientific questions will underlie the fundamental basis of using this system for diagnosis. Another very important principle is protein motion and harmonicity. How significant is that? And to the extent that these vibrations are harmonic, in other words, like a spring, a Hooke's law, or anharmonic, obviously will have implications for how tight the spectral lines are and how different it is from different proteins and so forth. The answer to this, it may depend. I mean, some proteins may be more harmonic, some proteins may be less harmonic. There's, of course, the issue of water and the solvent and so forth. So we don't entirely know the answer for this. And there's some suggestions that, again, it may depend. So then some more questions. How can one influence protein function by modulating their vibrations? This is unknown, although there was a study just a week ago out of Japan indicating that this is possible. I won't share that result today, but there are definitely beginning to have data or results that show the answer to this is yes. How far might the protein electrodynamic field, wave fields be expected to propagate? Did some simple calculations, maybe up to 1 to 2 millimeters. Again, this depends on the solvent and the environment and the strength of the protein vibrations and their electromagnetic capabilities and so forth, but that's roughly possible. So that means, could proteins communicate over a distance? In other words, the presence of one protein over a distance somehow communicate its presence to another protein. In other words, right now in that interactome I showed you early on in this presentation, the proteins have to physically bump into each other to, in effect, signal each other. But is it possible for that signaling to occur at a distance? The answer, again, to that is unknown. But of course, this electromagnetic mechanism would underlie that quote-unquote communication. A little bit more specific question, could protein electrodynamics mediate specific attractive forces between proteins? In other words, just like the van der Waals interaction is between atoms, which are induced dipole interactions, specifically London dispersion forces, could there be induced dipole interactions on a macromolecular scale? The force laws would be different. Obviously, they're based on electromagnetism, but they would have a different form. That would be a new kind of emergent force that could be very important in understanding life processes. So let's go back a little bit. What is terahertz? So electromagnetic energies between the microwave and the infrared. So microwave is lower frequency, infrared is higher frequency. Microwave is lower energy, infrared is higher energy. In many textbooks, you will see that there's nothing in between. In more advanced textbooks of electromagnetism, you'll in fact see a designation called terahertz, and people have called this the Terahertz Gap because it's very difficult to produce this energy, and it has not been readily used a lot. You've seen about microwave ovens, you have infrared cameras, but terahertz is a little bit strange, right? So until recently, it's been very difficult to engineer as it lies between the electronic and photonic domains of the spectrum. So this is a very fundamental issue. I asked the question last time, what is the difference between electronics and photonics? Some of you got the answer right, some of you did not. But here's the answer. Electronics produces electromagnetic radiation through the manipulation of unbound electrons, unbound meaning in metals. The technical term is the conducting band electrons. So the energy levels are very small, and that's why, of course, you have small energies. Photonics is the electromagnetic phenomena coming out of bound electrons, and the chemical term for that is valence band electrons. These are electrons that are more tightly bound to the nucleus, so the energy levels corresponding to their transitions would be greater, and that's why we are dealing with higher energies. So X-rays are these bound electrons in atoms. Obviously, there's things like Bremsstrahlung and so forth that relate to unbound electrons, but that's a different sort of phenomena. But when we're talking about materials, electronics is with unbound electrons from the low frequency, photonics with the bound electrons from the high frequency. Terahertz is right in between those. In other words, it's kind of not with unbound electrons, it's not with bound electrons. And the way we typically produce them, not always, but typically is we up frequency from the electronics way, or we down frequency from the photonics way. In other words, we have electronics ways to produce terahertz, and we have photonics ways to produce terahertz. Now, the interesting thing is that even though terahertz has been a kind of frontier, it is actually all around us, emitted by all living organisms, as we are all composed of proteins. And here's that protein as an example. And also water strongly absorbs terahertz, which presents both a challenge and opportunity. So this is a frontier in biology, as I've indicated, but it's also a frontier in the electromagnetic spectrum. So this is a graph of the electromagnetic spectrum. This is the frequency, 1 terahertz is right in the middle. This is the power output. From the low frequency side, that's the electronic side, and from the photonic side. So you can see photonic is red, electronic is gray here. And this is a logarithmic scale. You could see that the power output from these go way down at the terahertz. They're high power up here when the photonic is at its best. They're high power up down here when the electronics is at its best. When they approach the terahertz side, the power levels go down. So it's difficult to produce this radiation in the lab. There is an approach of what's called free electron lasers. That's not related to bound electrons, as I mentioned, a little bit like Bremsstrahlung and so forth. But in general, those produce the highest power terahertz. But in general, as I mentioned, we have this terahertz gap. So what are the natural sources of terahertz radiation? Remember that quote I started out with? 2 things fill the mind with ever new and increasing admiration and awe: the starry heavens above and the moral law within. That's Immanuel Kant, the German philosopher. So the 2 natural sources of terahertz radiation are the residua of the cosmic microwave, or the Big Bang, the residua of the Big Bang, which is the cosmic microwave background. Many of you have heard this, and the cosmic microwave background is a black body spread of radiation with a peak in the microwave. But of course, as a black body, it has a variety of radiation, and there's a significant component in the terahertz. And in fact, 10 billion years ago, when the Big Bang was still relatively fresh, the peak was not in the microwave, it was in the terahertz. And 10 billion years ago, it would have been called the cosmic terahertz background. But we still have a little bit of that coming from the sky. And the other source of terahertz are living organisms. It's not exactly the moral law, but we have a sense of moral, sense of ethics connected to life. And so life itself is a source of terahertz radiation. So the starry heavens above and the moral law within. So on a more realistic level, less philosophical level, we can look at the New York City Police Department. They have a system called T-Rave machine that detects terahertz radiation. Natural energy that's emitted by people can penetrate many materials. And they look for detection of a hidden weapon, such as a gun or a knife, because the person is composed of proteins. They are emitting this terahertz. It can go through clothing, but a gun is not made of terahertz. It does not, it's not made of proteins. And so it doesn't emit that, it emits infrared if it's heated or hot and so forth. So this contrast can indicate that. So there are two technical challenges to this whole issue, two major technical challenges. One is the production of terahertz sources of sufficient power and spectral resolution. The second is water absorption. Water absorbs terahertz. It's both an opportunity and a challenge. Now, you might be curious to understand why this range of radiation is absorbed by water, because I had argued that this range of radiation is specific to large molecules. Water, H2O, is a small molecule. And indeed, it has a spectra in the microwave, it has a spectra in the infrared, and so forth. But why should it have a spectra? Why should it have electromagnetic manifestations in what would be this macromolecular regime? Well, it turns out, as you know, we've talked about this before, water is hydrogen bonded, and it creates a whole network of hydrogen bonded molecules in water. And so this hydrogen bond network is kind of like a, what do you call, is kind of like a large macromolecule. And that's what's absorbing this electromagnetic radiation. So the concept of terahertz medicine is to do diagnosis, imaging, both anatomic and functional. So imaging combined with spectroscopy, and also some form of therapy, energy-based protein specific. So as I mentioned, the future is energy matter, and I argued this would be terahertz for this reason. That's the natural frequency of radiation of these proteins. And the three principles of terahertz medicine are some form of resonance with the protein, localization where those proteins are, and also functional activation or inactivation. So now we'll talk a little bit more about the science. And before we talk about the science, let's review, we've done this before, the difference between time domain and frequency domain measurements. So it's a fundamental difference approach to spectroscopy. In the time domain approach, we do a pulse that has a wide range of frequencies, and we extract those frequencies using a Fourier transform. It's a very elegant experiment. We can sample immediately, and of course it is the principle used in MRI. There's a radio frequency pulse, and many frequencies of protons are excited. Those protons release their energy. We eventually create an image based on that relaxation, geography, and so forth. The frequency domain measurements go one frequency at a time. That's the more classical, simple approach of doing, it's maybe not as elegant, but it's the more direct approach to doing spectroscopy. So we have time domain versus frequency domain. It turns out that about 99% of terahertz experiments that you'll see in the literature are time domain measurements that blast the sample with a wide range of frequencies, because many of these experiments come from the photonic side, and from the photonic side it's very easy to create a laser, a pulse, very short duration. We call them femtosecond pulses, and that can create radiation in the terahertz range in a wide swath of frequencies. So when I was at site at Samsung, in collaboration with Pohang Accelerator Lab and Hanyang University, I did some experiments on myoglobin and hemoglobin. Myoglobin is a single domain protein, oxygen storage protein. So here's the oxygen connected to a heme group, and hemoglobin has 4 of these subunits. Also binding to oxygen, 4 oxygens. It's used for obviously oxygen transport in the blood. So here's a scientific result based on that. There's a lot of studies here. I'm just summarizing the main one. This is the absorption in absolute units, and this is the frequency. So you can see 1 terahertz is around here. And we had 3 different proteins. bovine or cow hemoglobin, myoglobin, and human hemoglobin. So bovine, normal, and human, and red, green, and blue in this case. And the spectrum looks maybe not so impressive, but there are definitely differences. There's differences between myoglobin and hemoglobin. Myoglobin is the green, and it has more absorption at the higher frequencies. So that's here. And there's also species specificity. So the bovine is red, the human is blue, but you can see there's an opposite sort of effect. The human has more absorption at around 0.6 for 0.65 terahertz, and the bovine has less absorption at that point. So these are not artifacts. The very far region here is likely to be artifact, but down here we don't have artifact. And if you look really deeper down at lower frequencies, you see what's called a Stokes shift, especially with myoglobin and with bovine hemoglobin, where you have almost negative absorption. So what does negative absorption mean? Negative absorption is emission. In other words, these proteins are probably absorbing at higher frequency, higher energy, with the vibrations and emitting at the lower vibrations. And we call that a Stokes shift. Now, if you look at that spectrum, it looks pretty, how should I say, smooth. It's not perfectly smooth. So there's definitely features, but it's not the typical sharp resonance that you might have seen in infrared spectroscopy and so forth. But sharp protein resonances do exist. And there was a study earlier of lysozyme out of Buffalo, Dr. Andrea Markels, and they showed a sharp resonance of a lysozyme in the crystal form of about 1.5 terahertz. Now you'll see here degrees, and these degrees are not temperature degrees, but they are the degrees of the angle between the polarized terahertz beam and a certain crystal face. And so what this means is that this 120 degrees, that was the maximum absorption. So the crystal, which is an ordered array of proteins, is being aligned with the terahertz beam. And at a certain alignment, the dipoles are probably optimally aligned. And so we see this higher resonance. And so that definitely tells you that proteins have sharper resonances, at least this one. Now, of course, the fact that it's in a crystal means that many of these alignments are obviously in the right direction and so forth. So that seems a challenge because people are not crystals for medical applications and so forth. But it tells you that fundamentally sharp proteins exist. And there may be ways to extract those signals. Even more interestingly, in a follow-up study a few years later and recently, they looked at these motions as they probed them in the crystal, either without or with an inhibitor. And the overall transition of the dipole would shift from a hinging motion to a twisting motion, and the dipole or the direction of the overall motion would shift once it was bound. So in other words, the different functional states of the protein correspond to different motional characteristics. So the transition dipole shifts upon binding of the inhibitor. Now, other studies have shown proteins emit terahertz. This is Bacteriorhodopsin. It's a membrane protein that serves as a proton pump. Light comes in, and the retinal inside the protein will shift and pump a proton. And so we see proteins emit terahertz at 0.9 terahertz, as you can see here. Now, we had explored some of the fundamental physics going on as it relates to molecular dynamics and electromagnetic manifestations. What about the biology? What is the relationship between molecular dynamics and protein function? So this is that paper I was referring to, which looks at cancer. And some of you may be familiar with SARC. SARC is an oncogene, and wild type refers to normal, and the mutated form is the oncogene. When it's mutated, causes cancer. And this red is a heat map of the motion, and in other words, a simple way of showing where is most of the motion of the protein, and you could, so it's a simplification of this overall molecular dynamics, and you can see that that has been markedly changed between the wild type normal, non-cancer, and the cancer protein. So later on, I've collaborated not just at site, but afterwards with the Ohio State University, Dr. Kubalai Sertel, and we published several proceedings as well as articles on terahertz imaging of cancer. So this is a result from the IR MMW Terahertz 2013, IEEE, and then a published paper that followed. And to make a long story short, we did time domain spectroscopy, as I mentioned, but actually time domain imaging. So largely looking at water content, comparing, this is the optical images, microscope, and this is the terahertz, and differences of the absorption coefficient between normal and cancer tissue. So there are some ways to image, not in real time. This is pathological specimens. Now, based on that, we had an hypothesis that in Alzheimer's disease, which is a disease of amyloid deposition, it's a protein deposit as a first sign in the brain, and still a matter of controversy, what is the role of amyloid in the brain pathology? Is it a cause or is it a result? But the bottom line is ultimately you have more of this, you get tangles, you get neuronal loss, and ultimately dementia. So we did a study of terahertz imaging and electromagnetic model of axon demyelination. We did broadband or time domain terahertz spectroscopy. We did the reflection mode of samples. So we would irradiate with terahertz and see what the reflection was. We did fast frozen paraffin embedded normal and Alzheimer's disease hippocampus tissues. We compared with histopathology, and we also did an electromagnetic model of the myelinated axon. So these are very briefly some of the results. H&E is the stain, as we talked about at the beginning of the course, the optical microscopy, and this is the image, again, a broadband image. And to make a long story short, we see differences between Alzheimer's disease and control samples. The implications that we saw from this study are a strong correlation between Alzheimer's disease and terahertz image contrast. We want to refine the technology as applied to different types of neurodegenerative diseases. We saw in particular that white matter had more change than the gray matter when it came to the terahertz spectrum. And in fact, more and more studies are showing that even though Alzheimer's is death of cells, which is gray matter, some effect on the white matter may be a significant part of the disease. Maybe not the same as multiple sclerosis, but definitely perhaps underlooked, and our results suggest some significant white matter changes. So also the fact that our study is sensitive to demyelination suggests that we have additional application to multiple sclerosis and other myelin disorders. And as I've implied, continuous wave techniques to obtain even better step specificity is based on protein electrodynamics. Terahertz medicine concept may be important for this. And a final sort of collaboration that I've been involved in when I was at Samsung and with the University of Texas, Dallas, is an integrated terahertz source and sensor. This is Dr. Kenneth O, who works at UT Dallas. And what this is from the electronics side, a chip that both produces terahertz and absorbs, or senses it, I should say, detects it. And this miniaturization and lower cost gives possibilities for what we would call a Star Trek tricorder-like medical diagnosis device. We'll talk about this concept more later. So the overall conclusions from the science section are, in terms of proteins, tissues, applications, and technology. Proteins, definite signals are observed with proteins. Continuous wave spectroscopy may be able to detect these better, but these are low power. We've done some work, I have a patent with MIT, 2D terahertz spectroscopy in order to tease out some of these signals. most low frequency emissions are in this sub 1 terahertz range. That's a very important conclusion. Now, in terms of tissues, different types of tissues can be distinguished via terahertz imaging. Normal and pathological tissues can be distinguished, and we've demonstrated applications in cancer and Alzheimer's diseases. Now, in terms of applications, we can split them into two parts. Imaging, essentially using the water contrast for imaging, and spectroscopy, focusing on proteins. It is the ideal technique for spectroscopy because it's without a label, it's native, and it's non-ionizing. And finally, some technology implications. High power, pulse, continuous wave, or multi-frequency are key elements from an engineering perspective. We want to optimize these to the sub 1 terahertz range between 100 gigahertz and 1 terahertz. And of course, miniaturization, for example, by Dr. Kenneth O's University of Texas platform via silicon-based CMOS platforms. So water penetration, we mentioned, is a problem. The best range, actually, so there are 4 ways we can solve this. One is by going into the sub-terahertz. Second is by tunability, using continuous wave, specific water windows, or aiming at specific water windows. You can see that here. Using pulsed radiation within 10 picoseconds to minimize water relaxation effects, and also Beer-Lambert higher power. This is just a diagram that shows lower water absorption in sub-terahertz range. So based on the biology, back to the physics, as I mentioned, electronics is unbound electrons, photonics are bound electrons, and these are the different electronic sources and photonic sources: solid state, vacuum, direct lasers, electro-optical conversion. But I think that the best approach for biophysics, medicine, is going to be the solid state, because the vacuum electronic sources also produce wide range time domain or broadband spectrum. So solid state is very critical. So we go to the final part of the presentation and lecture, and I'll go through this very quickly. Our applications. Talk about why, we'll talk about new medicine, potential applications, terahertz light switch, electromagnetic Taxol, neuromodulation, Bacteriorhodopsin switch, antibiotic resistant antibiotics. I know that sounds complicated. Drug screening, protein-protein interaction affinities, a little bit about terahertz, Star Trek tricorder, waves, and COVID. So, as I mentioned, medical imaging, we have no new modalities for over 30 years. We lack of specificity is a key limitation. Biopharma innovation has stalled, unsustainable costs. Technology evolves, so energy on matter will be the future paradigm of medicine. Why? Because we'll have greater specificity, more non-invasive, greater effectiveness, lower cost, more rapid therapy development, convergence of medicine and surgery. So this has been happening more often. We have new medicine. Take electrified medicine seriously in Time magazine. Google spin-off Verily, Galvani Bioelectronics between Verily and GlaxoSmithKline. And there are groups around the world, research groups focusing on electrodynamics. Notice this is a group out of Prague in the Czech Republic. Michel Cifra, who's also a friend of mine. Sub-terahertz, protein, control function field. Those are very key points. So people are definitely starting to do this. So just an overview of some applications. Electromagnetic Taxol, talked about for cancer. Antibiotic resistant antibiotics for microbial diseases. Neuromodulation for Alzheimer's, diabetes, wound healing, and more. It's a platform technology that will revolutionize both diagnostic and therapeutic medicine. What is a terahertz light switch? Well, this is not really an application, but it will be more of a proof of concept. So you take, we know about bioluminescence, which are the jellyfish and the fireflies. We've talked about that in the course. So you have a cell-free bioluminescence extract, terahertz frequency scanning experiment, observe for on-off effect, correlate with molecular dynamic simulations. In effect, you turn on the light using terahertz as a switch. Cancer and microtubules. So the most powerful cancer medicine is actually called Taxol. It affects the polymerization and depolymerization of microtubules. Microtubules are involved in cell division. And so the chemical blocks this cell division, But the problem with the chemical or the drug Taxol is it's very toxic because we need dividing cells normally, not just in cancer, the cells are dividing, but in our intestines, in our skin, in our bones, bone marrow, the cells are dividing a lot and continuously dividing, producing new skin cells, producing new gut cells inside as we're eating, and it has to be regenerated, producing new blood cells in the bone marrow. So when people take this powerful medicine, it affects all of those functions, and that has severe side effects and can indeed even be fatal. But if there was a way we can electromagnetically affect Taxol, which is a protein and also has a dynamics, and affect it locally, that would be an electromagnetic Taxol. So the experiment would be to take a cancer cell line, determine the terahertz spectrum of tubulins, set up experiments, control Taxol, terahertz, analyze tumor growth, histology, light microscopy, cell cytoskeletal imaging. Another example would be neural modulation. I have affiliation with the University of Melbourne. They have 3D printed nerve cells. Maybe we can do terahertz on that and see how nervous cell development happens. Bacteriorhodopsin, as I said, is a light switch or proton pump, switched on by light. Fadel Samate is a friend of mine, also a former colleague from France. He's now in Okinawa, and there might be a way to turn on that light switch. That could be a way of biocomputing, bioelectronics, proton pump switch. Now, Bill Gates has talked about pandemics, but there's also the concept of pandemics related to antibiotic resistant bacteria. Now, viruses are very dangerous, can be very dangerous because there are no antibiotics for them by definition. Bacteria are not so bad because we can kill bacteria with antibiotics, but if the bacteria are resistant to the antibiotics, we could have a devastating pandemic from these antibiotics. So a post-antibiotic era in which common infections and minor injuries can kill is a very real possibility for the 21st century. So these are different forms of antibiotics. You've heard of penicillin. They basically bind to proteins and inhibit these proteins. We could create an antibiotic resistance terahertz ray that kills bacteria, and if it becomes resistant, we just switch the frequencies a little bit to improve that function. So with some work potentially with the Institut Pasteur, drug screening, we can have terahertz frequency screening to answer this question: can one influence protein function? So they have robotic screening mechanisms. They have a disease model. They drop different drugs, but instead of dropping different drugs and trying those out and do drug screening, we can have terahertz screening to identify what would be the best frequencies. We can also answer these questions. Could proteins communicate over a distance? Could protein electrodynamics mediate specific attractive forces between proteins? Through machinery, intermolecular BRET, quantifying protein-protein interaction affinities, Institut Pasteur has some capabilities in that. But if we can identify that protein-protein interaction being influenced, that would be very powerful. So let's go to COVID now. What is a virus? A virus is genetic material contained within an organic particle that invades living cells, uses the host's metabolic machinery to produce new virus particles. So you can see the virus here in the yellow, color enhanced, and this is a cell that it's being infected. Are viruses alive? Well, let's look at the SARS virus. As I mentioned, it's genetic material contained within organic particles. So this virus has three parts from inside to outside. Nucleic acid or RNA on the inside, number one, lipid membrane covering that, and then finally a spike protein, number three on the outside. So the nucleic acid inside is related to mutation, genetic material, used for testing, etc. The lipid envelope, the kind of grease, determines the environmental viability. So soap and alcohol obviously disrupt this membrane. And the spike protein, number three, most importantly, determines the target, is blocked by antibodies, and also used for testing. So remember I mentioned the question, are viruses alive? No, there are only two ways to get rid of the virus. You can either physically destroy it, or you can have it cleared by the immune system. So there are no antiviral drugs that kill the virus. So we need a new method to do this. So one method is to use electromagnetic radiation to destroy and inhibit those proteins from binding or having their activity. So another aspect is those surface proteins have their own particular vibrations. A handheld thermal scanner, everybody's seen that. We could also envision, not in the infrared, which is what's used in the handheld thermal scanner, but a terahertz and tuned to those specific frequencies for a handheld COVID scanner. So terahertz physics has been a challenge, but why now? There's been growing interest, it's becoming mainstream with medical and industrial applications, better performance of the technology, detector technology, successful miniaturization, and very importantly, decreasing costs. So we can imagine a Star Trek tricorder. The cell phone was very much anticipated by the communicator. It led to the mobile phone. So the tricorder here, which was a medical device, a sort of diagnostic device. We can imagine a quadcorder that could be also doing treatments. And finally, I've actually written a book about this concept called Waves. This is a customer review from Josh Steinfeld, introducing an idea to the world. Read this novel as strategy, a strategic approach to introducing an idea in the world, an idea that has taken decades to mature, due to the limits of technology, an idea spreading across the globe. So to help bring this idea out, not just the technological aspects, but the social dimension and social awareness, because it involves a paradigm shift. I've written a novel available on Amazon for this purpose. So very quickly, some closing thoughts. I've given this presentation around America, in Europe, in Asia, in Australia, and now today I'll be giving it in Turkey or by webinar. And Isaac Newton, who was the founder of modern physics, was actually very interested in biology. And at the end, the general scholium, at the end of his Principia, where he outlines the laws of physics and so forth, he writes about sensation, the limbs of the animals moving, the solid fibers of the nerves, but these things cannot be explained in a few words. There is not a sufficient number of experiments to demonstrate accurately the laws by which this electric and elastic spirit operates. Now, Newton was not thinking of proteins, but I like this phrase, electric and elastic spirit. Another hero of mine, Richard Feynman, some of you may be familiar, famous physicist, founder of quantum electrodynamics, wrote that everything that living things do can be understood in terms of the jigglings and wigglings of atoms. That was in lecture number 3 of the first volume. And finally, I met Martin Karplus at his 2014 Nobel Prize Celebration Symposium. And there were many students giving seminars, and I was one of them, former students, I should say. And I asked him, what would you suggest? And he said, I would do the experiment on an enzyme. If it works, it would be significant. So you might have seen some of these spectra and say, oh, that's not very impressive. You know, how could that become medical technology? But as you know, in the beginning, technology is not always pretty. This is the first airplane with the Wright brothers. But dreams can fly, moonshots can become reality, and even Mars shots. So that's the presentation. That's our lecture. That's the summary of bioelectronics. And I know it's getting a little bit late, so we can stop for questions. And I want you to focus